This video explains how the DIPPR evaluation process goes beyond automated methods by using expert review and how this drastically improves the accuracy of the database. One of the facets of the DIPPR evaluation process that greatly contributes to the accuracy and thermodynamic consistency of the database is expert review. Project staff use a heuristic-based approach to evaluate existing experimental data and predict values for properties when no experimental data exist. However, before addition to the database, this entire work is subject to separate review by 3 experts in thermodynamics. The value of this expert review process is demonstrated by the compound tetrasilane. As you watch, you will see how the expert review changed the results of the heuristic-based evaluation to give an accurate thermodynamic picture of this compound. Here you see experimental vapor pressure data as green points. Notice that they span a wide range of temperatures and are fit well by the correlating equation. No heat of vaporization data exist for this compound, so the staff used the Clapeyron equation to predict the property from the vapor pressure. Despite the thermodynamic rigor of this prediction, the resulting heat of vaporization data are of some concern. Heats of vaporization typically scale with this relationship. The Clapeyron-derived data have a much higher exponent. Moreover, the data do not follow the rest of the family at low temperature. Notice the difference in low temperature slope from that of silane, disilane, trisilane, and pentasilane. One other property, the liquid heat capacity, was also problematic. The liquid heat capacity is rigorously related to the vapor pressure and heat of vaporization through this equation. Unfortunately, the result is unrealistic. Liquid heat capacities rise rather than decrease as the system temperature approaches the critical temperature of the compound. To correct these problems, the staff member overseeing this compound decided to not trust the experimental vapor pressure data and instead predict the value using the Rydell method. The yellow line shows the results. Using this predicted data for vapor pressure appears to fix the heat of vaporization obtained from the Clapeyron equation. Notice the scaling exponent is now exactly 0.38, the expected value, and the low temperature slope now follows the family trend. Finally, also notice that the liquid heat capacity no longer curves down at high temperatures. At this point, the staff completed the compound and sent it on for expert review. The reviewer did not like throwing out the experimental vapor pressure data as it came from multiple reliable sources. Based on previous experience, the reviewer also knew that the value of the critical pressure can drastically alter the vapor pressure, heat of vaporization, and liquid heat capacity predictions. The reviewer went back and looked at the critical pressure. No experimental data existed for this property, so it was predicted using established techniques. Here you see the 5 methods approved by DIPPR to predict critical pressure. Notice the variance in the values. To select the correct method to use, the staff evaluate how well each method performs for compounds with experimental data and from the same family as the compound under review. This analysis showed that the Ambrose method predicted the critical pressure of other linear silicon-based compounds to within about 5%, while the Wilson-Jasperson method was about 8%. Realizing that a higher critical pressure would improve later predictions, the reviewer chose to accept the Wilson-Jasperson value and recalculate the other properties. Here are the results for vapor pressure. Notice that the Rydell prediction now passes right through the data, which were then included in the correlation. With the new critical pressure, and accepting the experimental vapor pressures, the heat of vaporization is more realistic and follows both the scaling law and the family trends. Finally, the liquid heat capacity also displays the correct behavior at high temperature. Expert review of compounds is one way that DIPPR ensures it is the gold standard for thermophysical property accuracy. DIPPR has an extensive heuristic-based methodology for the initial compound review, but empiricism alone often fails to recognize the intricacies relating thermodynamics, regression, and prediction. Expert review overcomes the failings that can occur from the initial, more automated approach.